Okay, hello. So this video is going to go over a couple additional examples of nodal analysis. So for this first example, we're going to solve the given circuit, which I've already labeled the ground node, and for nodal voltages VA and VB. In other words, this circuit has three essential nodes. Two of them are non-reference essential nodes called A and B, and one of them is a ground. Okay, so we're going to first order guesstimate would be we need two KCL expressions at A and B in order to solve. But I also want to note that nodal voltage VB can be described in terms of nodal voltage VA. And that's because of this relationship between VA and VB that is dictated by the connection between this 10-volt source. So we could write that VB is simply 10 volts higher than VA. VA plus 10 equals VB. Likewise, we could rewrite this as VA equals VB minus 10, whatever you prefer to do. Okay, so first our KCL at node A. We're going to again assume all currents are exiting. So first, the current through the 1 k ohm resistor will be described as VA minus 5 divided by 1 kilo ohm. The current through the 4 k ohm resistor would be described as VA minus 0 over 4 kilo ohms. The current through the 10 k ohm resistor is going to be described by VA minus VB over 10 kilo ohms. So that's 1, 2, 3. We also have one more branch. And in this branch, we only have a voltage source. We don't know we don't have Ohm's law or some other IV relationship to describe the current. So in this case, we actually have to define an unknown current. I'll just draw the arrow there and call it IX. I don't know what IX is, so I'm just going to write plus IX and then set this whole thing equal to 0. That IX has to be there though because I have a branch, therefore there must be current. Okay, so next our KCL at node B, excuse me. So the current through this 10 k ohm resistor, assuming it's exiting that node, would be given as VB minus VA over 10K. Current through this 10 kilo ohm resistor would be given as VB minus 0 over 10K. And then again we have a current through this branch. Now the current in this case is defined for us. It's actually going into that node. Therefore I'm going to set this whole equation equal to current IX. Okay, so now let's examine our system. I've got two KCL equations in terms of VA, VB, and IX. So I have three unknowns, but I have a third equation right here relating VA, V, and VB together so I can solve this system. If I didn't get that relationship pinning VA and VB together, it wouldn't be solvable. So solving this system, I get that VA equals 2.96 volts, VB is 10 volts higher at 12.96 volts. And I could solve for IX if I want to. It's not asked for in this question, but could be done. And that's our result. So in this last example, we saw something interesting in that we saw a voltage source that wasn't connected to a known voltage or a ground. So in this case, there's always these two steps that we should go with in order to deal with that. The most common mistake is that I see students assuming that there is zero current going through that voltage source. I've said this before, and I'll say it in this context again, that we can never assume that there is zero current going through any element. So in this case, what we do is define an unknown current through that source. That's what I defined as Ix in the previous example. Once I do that, I can construct a KCL at either of those nodes to eliminate that current. And also remember that voltage sources always constrain the relationship of voltage between two nodes. For example, if I have the voltage source 5 volts connected to nodes VB and VA, as noted here, then I can always write VB in terms of VA or VA in terms of VB. So kind of do this similar to the way you would do a KCL, but you'd start, say, VA plus 5 volts must equal VB, or you could write that VB minus the 5 volt potential is going to be equal to VA. However you write it, it doesn't matter. Just noting that VA and VB are not unique. They are pinned together by this 5 volt source. The relationship is decided for you. This provides some interesting implications. In the last example, we noted that relationship and it helped us get rid of that unknown Ix. But noting that this occurs, we can actually do something interesting in the analysis. We'll work this example again and noting that interesting relationship between the two nodes. Okay, so let's solve this example again. And so again, at the very beginning of the problem, we might identify that VA and VB are related to each other by this 10 volt source. And so in this case, I would say VB is going to be VA plus 10 volts. So since we've identified this is what we actually call a supernode. In other words, these two nodes, A and B, are not actually unique essential nodes. They're related to each other. And when we have this special scenario called a supernode, we can actually draw them in kind of a little bubble, the way I just did it just here in red, and we can write a single KCL at the supernode, noting that all currents going into the supernode must also equal all currents going out of the supernode. So let's do that. So we're going to do a KCL at supernode AB. Again, I'm going to in this case, instead of assuming all currents are exiting, which is what I always want to do, I'll show you, you don't have to do that. You can draw the currents on there. So in this case, I'll draw some currents just to illustrate a point in a moment. So in this case, assuming the currents drawn on the chart as follows, first, the current through the 1K ohm resistor will be given as voltage VA minus 5 over 1K, just as in the previous example. The current through the 4K ohm resistor is VA minus 0 over 4K. And the current through the 10K ohm resistor is VA minus VB over 10K. Again, I'm going to keep going and do only what's going in and out of the supernode. So now, instead of writing the current here, which is inside this supernode, I'm not going to draw it. I have another current coming out of the supernode, which is the one through the 10K ohm resistor here. So plus VB minus 0 over 10K. And that must equal everything going into the supernode. And I've actually drawn one current going in. So it's coming out on this side and going back in on this side. So I must say equal to the current going in, which is VA minus VB over 10K. Now note in this case, the VA minus VB over 10K shows up on both sides of the equal sign, so they cancel out. And this equation simplifies to VA minus 5 over 1K plus VA over 4K plus VB over 10K equals 0. So I have one KCL equation in terms of VA and VB, and I have the constraint of VA and VB, Those are my two equations to solve for my two unknowns. And I get the same solution as in the previous slide. So in effect, what we've done with a supernode is we've taken the two KCL expressions at nodes A and B, and where in the previous example we wrote them in terms of current Ix, if you do a substitution of one of those equations for Ix into the other, you end up with the exact same expression that we derived in this example. So the supernode is doing that substitution for us. Note that the book, when describing supernode, will go ahead and draw this 10k ohm resistor in this supernode, and that's because of the observation that the current through the 10k ohm resistor is exiting and entering the supernode at the same time. Therefore, will cancel out and not end up in our final expression. I like to draw it this way just to illustrate why you can ignore the current through the 10k ohm resistor as being irrelevant to the problem. Okay, so what you've seen in this short video is two ways to solve the same problem, one with basic nodal analysis and one with nodal analysis noting a supernode. What I would also encourage you to do is solve this example again on your own, but changing the location of the ground from the bottom here to either node A or B. So change the location of the ground, resolve this circuit, you should get exactly the same solutions. I think that would be excellent practice. Thanks.